On October 3, 2025, the interstellar object 32/Atlas passes a mere 0.2 astronomical units from Mars. While numerous telescopes are primed for action, the sole publicly available proof emerges from a weak signal pulled from Perseverance's nighttime sky photos by a pair of separate researchers. Despite anticipated releases from Mars satellites operated by NASA, the European Space Agency, China, and the United Arab Emirates, an odd hush prevails, turning the most significant extraterrestrial close-up since Oumuamua into a puzzle reliant on unconfirmed glimpses. Could this be our first real peek at an interstellar comet's secrets? Or will this nearest inspection forever evade capture? The implications for planetary research and humanity's preparedness for future arrivals have reached unprecedented levels. Mark October 3, 2025, 3I/Atlas hurdles by Mars at less than 0.2 astronomical units, roughly 29 million kilometers away. By cosmic distances, that's remarkably near, setting up an exceptional setup for astronomers studying planets. For the first time, an interstellar visitor nears a world with such a synchronized fleet of spacecraft and landers ready to scrutinize it. The Mars Reconnaissance Orbiter, ESA's Mars Express, UAE's Hope Probe, and China's Tianwen-1 all got urgent directives to observe. Teams from each project reshuffled timelines, updated orbital paths, and geared up to document this outsider from outside our solar system as it grazed Mars' path. The moment was brief. At peak proximity, 3I/Atlas streaked across the Martian heavens faster than any typical comet. The setup demanded precision. Just a slim time frame, mere days, with the target quickly fading into solar brightness. Scientists saw the potential vividly. Orbital snapshots in fine detail might uncover the comet's makeup, possibly spotting detached pieces. Should the core start fragmenting, instruments could detect distinctive molecular traces, setting interstellar frosts apart from homegrown ones. From ground-based explorers to far-orbiting craft, every tool was stretched to its max. The math was straightforward. One precisely captured photo or reading could resolve debates on the comet's birthplace, composition, and the forces molding extrasolar rocks. The rewards? A shot at examining pristine interstellar stuff, validating ideas on world building, and directly assessing traits of something that traveled light years to arrive. As the pass occurred, excitement built steadily. Everyone anticipated a deluge of info and maybe a sharp image of the enigma. Yet all that Perseverance's Mastcam-Z captured in the Martian darkness post-closest approach was a dim, spread-out trace. The initial duo to isolate and openly validate this find were Stephen Burns, a geologist and veteran hobbyist processor, and Simon Stimson, respected in astronomy imaging for his rigorous methods. Operating solo, they grabbed the unprocessed Mastcam-Z shots from NASA's open repository right after transmission. Their method aimed for simplicity but required meticulous care, merging scores of extended exposure frames, syncing to the Martian stellar backdrop, and gradually filtering out interference until a faint luminous spot appeared right at the forecasted spot. The outcome isn't flashy. It's a processed composite, labeled and circulated digitally, displaying a tiny, somewhat blurred and encircled by a soft haze. That hazy envelope, vague and nearly blending into the surroundings, aligns with 3I/Atlas's anticipated location based on prior trajectory models. Nothing explosive, no abrupt flare, just quiet validation that the intruder traversed Perseverance's sight line precisely as predicted. Burns and Stimson shared their results prudently, highlighting the detection's faintness and lack of discernible details. Their marked visuals, uploaded to X and Blue Sky, featured projected comet tracks and access to their processing code, welcoming review from fellow enthusiasts. In the realm of planetary studies, such a spotting goes beyond mere technique. It proves that, despite holds on info and institutional quiet, diligent work with accessible records can produce genuine insights. That subtle core glow in the Perseverance composite serves as the lone ground-level proof of 32/Atlas's transit. Not a game-changer or letdown, but proof of what's achievable when shared resources encounter dedicated inquiry. The verifiable route to spotting 32/Atlas starts with Perseverance's Mastcam-Z exposures, each a 29-second shot under Mars' nocturnal vault. October 3rd yielded 36 such images. October 4th added 40. Experts pulled the unrefined files from NASA's database, matching each observation to the nearest dark reference to eliminate detector artifacts 1 pixel at a time. Then came even-field adjustments via reference docs to adjust for varying pixel responses and lens contaminants. Aligning the frames posed the subsequent challenge. Each image's star the rover's field of view was calibrated using a Mars-centered stellar reference catalog, accounting for its precise alignment and the gradual shift in the Martian heavens. Fine-tuned subpixel shifts guaranteed that even the dimmest stars aligned perfectly in the combined images. Techniques like outlier removal, sigma clipping, and median smoothing eliminated cosmic ray strikes and intermittent faulty pixels, while masks concealed any lingering imperfections. Armed with this refined and synchronized dataset, researchers combined the frames via both median and average methods to optimize the signal-to-noise performance. They modeled and removed the ambient sky glow, uncovering faint objects hovering near the sensitivity limit. This final composite revealed a subtle, somewhat blurred point at the anticipated position of 3I/Atlas, consistent with pre-encounter predictions to within astrometric tolerances. Photometric analysis verified the feature's intensity, surpassing the composite's background noise by a robust statistical factor. The findings surpassed the conventional signal-to-noise benchmark and underwent independent confirmation through publicly available code, with every calibration procedure and settings file shared openly to enable verification. Overall, this yielded a clear, repeatable pipeline built to endure rigorous examination and avoid mistaking random fluctuations for genuine detections. Speculation outpaced the evidence. As soon as subtle traces from Perseverance's Mastcam-Z started to leak out, assertions of vivid, distinct lines in additional rover photos followed suit. The buzz peaked around a slender trail in a Perseverance Navcam image dated October 3rd, touted as naked-eye evidence of an interstellar intruder. Planet enthusiast sites soon overflowed with marked-up captures and conjecture-filled discussions. Yet the details failed to align. On Planetary Emily, the geologist famed for meticulous orbital calculations, inputted the position into JPL's Horizon system. The trail's trajectory and schedule coincided with Phobos, Mars's innermost satellite, to less than a degree's deviation. Its velocity, angle, and stretched appearance all mirrored Phobos's forecasted nightly path during an extended Navcam shot. Word of the conclusion circulated rapidly. That popular streak turned out to be no 3I/Atlas, just a routine moon in transit. A fresh wave of hype targeted an October 2nd Mastcam-Z image, featuring a luminous, swift dash that appeared baffling at first glance. Hobbyists quantified its angular speed and contrasted it against the forecasted celestial track for 3I/Atlas. The outcome was unmistakable. The dash traversed the view in under a second, far quicker, by at least a factor of 10, than the comet's projected pace. The light pattern implied a close-range item or camera glitch, rather than a distant interstellar body 30 million kilometers off. On Planetary, Emily and fellow experts shared comparative overlays highlighting discrepancies in pace and orbital projection. The broader observer network embraced these evaluations, redirecting attention to the subdued, anticipated trace in the processed composites. This saga drove home a key insight. In the realm of planetary exploration, any anomaly requires thorough vetting, orbital alignments, motion assessments, and flaw inspections prior to jumping to conclusions. The resources are accessible, the methodology open, and the collective, once engaged, can dismantle falsehoods as swiftly as they emerge. Martian satellites were primed for action. The Mars Reconnaissance Orbiter, boasting its HiRISE instrument, held potential for the crispest snapshots yet of an extraterrestrial wanderer from beyond our system. With its tight observational window and keen detectors, each shot hinged on spot-on aiming and synchronization. ESA's Mars Express, armed with multispectral cameras and the Omega spectrometer, brought complementary capabilities, sweeping surveys for evaporative compounds and material signatures in the surrounding haze. The Trace Gas Orbiter, featuring Nomad and Cassis, was set to gather both visual data and detailed spectroscopic readings, hunting for molecular markers that set 3I/Atlas apart from native icy bodies. The UAE's HOPE probe and China's Tianwen-1 broadened the watch, adding panoramic surveillance and possible extraspectral insights. The operational potential was tangible. These craft enjoyed superior positioning to track 3I/Atlas at perihelion, free from the solar interference hampering Earth-based or nearby observatories. Conceptually, HiRISE might discern the haze's form or detect debris if fragmentation occurred. Omega and Nomad, optimized for subtle vapor tracing, could snare hints of exotic chemicals or unusual atomic variants, paving the way for a major chemical revelation. Each sensor group adjusted their configurations to boost signal clarity, weighing capture duration, data compression on board, and hazards like overexposing sensors or overshooting the object. No unprocessed visuals. By October 7th, 0 detailed images or spectral profiles from Mars satellites had entered open repositories. Standard previews, media updates, and even preliminary previews stayed restricted or held up by analysis delays. The quiet stems not from inaction or mischances. Rather, it arises from data holdover rules, calibration amid delays from data queues, and the concurrent federal government furlough. The global community holds its breath, aware that the pivotal observations may already be secured, awaiting rigorous institutional vetting. Directing a probe toward a dynamic object billions of kilometers distant demands precise risk assessment. The orbital forecast for 3I/Atlas, outlining its anticipated spot in the Martian heavens, received frequent updates, daily or even hourly, as fresh observations sharpened the comet's path. Missions depended on these shifting estimates to outline their photography protocols, yet the procedure demanded manual oversight rather than automation. Probes such as the Mars Reconnaissance Orbiter and Mars Express needed to pivot from standard objectives, sometimes shifting by multiple degrees without immediate confirmation of alignment on the correct celestial sector. Sensor groups set up shots in blind operation, rendering each photo an act of optimism. Aim, capture, and cross fingers that the target traversed the viewfinder within the allotted interval. Coordinating the deep space network introduced further vulnerability. Transmissions from Mars require constant bargaining. Research outputs from various operations, standard status updates, and critical directives vie for scarce channel capacity. Even flawless execution might leave unprocessed visuals stored aboard for hours or days, queued after essential signals, or stalled by station readiness. An overlooked slot or slight deviation in the orbital data could spell the gap between a landmark find and an empty shot. In truth, without live monitoring, retries, or on-the-spot validation, confirmation arrives only upon data's return to our planet. Such hurdles stem not from flawed strategy or gear shortcomings, but from the inherent boundaries of remote space endeavors, where each scan involves equilibrium. Forecast, align, and anticipate the relay. The razor-thin divide between success and oversight is woven into the fabric. For 3I/Atlas, anticipation builds not from concealment, but from the relentless nature of planetary surveillance, as unyielding as space's vastness. Solar positioning imposes a stark boundary. With October progressing, 3I/Atlas nears superior conjunction on October 21st and 22nd, aligning nearly straight behind the Sun from terrestrial perspective. By mid-month, the angular separation drops beneath viable thresholds for telescopes. This observational pause isn't a directive, it's dictated by celestial paths. From mid-October until early December, terrestrial and numerous orbital facilities must halt activities. Perihelion, the comet's nearest solar pass, occurs on October 29th and 30th, smack in this intense light zone. The comet's peak vitality, potential surges or splits, unfolds unseen from Earth. At the same time, quiet from Martian satellite crew signals procedure, not withholding. JPL's photo and adjustment specialists navigate intense checks. Each unrefined image demands scrutiny for radiation strikes, faulty sensors, and alignment slips, which intensify when pursuing a dim, swift traveler. Routine processing, optimized for static Martian terrain, falters as the entity zips across the view at dozens of kilometers per second. A slight offset in layering or overlooked flaw might spawn illusions, spurious pieces, or erase genuine signals. The math is straightforward. Issue a raw image and invite baseless rumors, or hold for thorough analysis and draw criticism for slowness. Agency holds, processing delays, and the intersecting shutdown all exacerbate the jam. Currently, the wait persists not for deception, but for robust, examinable proof. Solely, then will subsequent visuals carry credible weight. The prevailing theory holds firm. 3I/Atlas qualifies as an authentic interstellar wanderer, abundant in carbon dioxide, showing only subtle or absent dicarbon, the typical greenish halo indicator in solar system icy bodies. Initial analyses suggest a reactive blend and, in certain readings, elevated metals such as nickel, though no validated structural analysis has emerged. Conclusive validation awaits not conjecture, but tool-confirmed readings or robust, high-fidelity temporal records to affirm or refute the organic comet model through molecular precision. As Earth observatories remain sightless until early December, focus turns to scant resources primed for surveillance. SOHO's LASCO C3 coronagraph will probe the solar haze until late November. Its faintness threshold stands at magnitude V8 to V9, so merely a sharp flare or unforeseen surge could render 3I/Atlas visible. ESA's JUICE probe, en route past Jupiter, might snag a narrow opportunity in early November for wide-field captures. Outcomes hinge on positional timing, task slots, and if the comet's dimming stays detectable by its gear. No official pledge or timeline has appeared. The timeline is straightforward. Scan SOHO C3 feeds from late October to late November. Track ESA and JUICE updates for potential EA by the end of November or the start of December. Ground-based observatories on Earth will once again have a clear view, allowing major facilities and dedicated hobbyists to potentially rediscover the comet if its glow is sufficient. Confirmation standards are firmly established. Nothing short of solid observational proof, such as spectral signatures, clear high signal-to-noise photos, or sequential data captures, will resolve the debate. The takeaway is crystal clear. Lacking additional spaceborne instruments, future interstellar objects might slip by undetected, concealed within awkward orbital alignments. So far, the sole publicly available proof comes from a dim, composited shot captured by the Perseverance Mastcam Z, processed and shared by outside experts. No detailed visuals or analyses from Martian satellites have surfaced yet. With Earth now facing a data blackout from solar conjunction, updates from NASA, ESA, and similar organizations are still forthcoming, leaving key insights into the object's makeup and form elusive. Until fresh visuals or readings appear, be it from SOHO JUICE or the restart of terrestrial monitoring come December, the most compelling clue persists as that one subtle trace. Thus, the mystery surrounding what sets 3/Atlas apart lingers unresolved.